Hi, my name is Twisha, and this is my final lab for Physics 2. The goal of this experiment is to observe how Faraday's law is present in a system of a bar magnet falling down a tube of aluminum foil. So we're going to collect both observational data and then also model this computationally and compare how they look. So what our findings was that an average time of the magnet falling down was 1.64 seconds, and with our calculated dipole, the time on our computational model was 1.4 seconds, and if we change the dipole to match the time, the dipole was 2.06. Here are the key concepts and equations that we need to understand. So first of all, we just have what magnetic flux is. Then Faraday's law takes that to the next level, and they observe the change in magnetic flux and how that creates an EMF. We took a derived equation from Faraday's law to model what's going on, and then also we just kept our force equations and force on a wire equations in the back of our mind because we are still looking at that. So here's our assumptions and models. As you can see, we have our falling magnet down the tube. Our system's the falling magnet, and the surroundings is pretty much everything else. So our mu is pointing downwards, and as you can see, we have two red arrows. One is the force that the tube is putting on the magnet, and one is the force that the magnet's putting on the tube. So those are in equilibrium, and that's why it's taking like a long time to fall down. But then we also have the additional force of gravity. Essentially, in our procedure, we dropped the magnet down the tube and we took a video so that we could scrub through the video and figure out how long exactly it took for the magnet to fall down. Then we did this 5 times and computed the average, and then we moved on to our computational trial. So from our 5 trials, we found that the average time from the magnet entering and leaving the tube is 1.64 seconds, and then we also recorded the length of our tube, the radius, the magnetic dipole that we calculated, and the mass of the magnet. So then we move on to our computational model, and it's a lot of like heavy coding, but all we have here is our physical constants, and we just initialized our graphs, and we are creating the tube of our aluminum foil. A lot of this section was just creating the tube that we were going to throw our simulation into, and then also at the bottom I edited to create our bar magnet and reflect the constants and the mass that we calculated. So what we did here is we used our code from lab 3, where we essentially created the magnetic field and we made it for our dipole, and then we also edited that to create a function to calculate our magnetic flux. So then we got into our entire simulation loop, so we just kept repeating this process. So what we did is we updated our time, we updated our position, and then we calculated our continuing forces, so our gravitational forces, and then also the forces on the magnet and on the tube, and we just kept doing that over this loop. And then the final part of our loop was obviously calculating our B field, so we updated that over time as well. And then we just kept updating our velocity and position, and then once the magnet was out of the tube in this computational model, we updated the time and printed it out. So after we completed our code, we tried to tweak our code and to see how our results would change over time. So the first one, we took our mu that we calculated, which was 1.952, and we tried to see how long that would take in our computational model. So we saw that the time was actually shorter than expected, and it was 1.472 seconds. Then for our second trial, what we did is we tried to align our time with what we observed in our physical model. So we were tweaking our mu value, and we found that our mu to match our time would be 2.06. So this can mean a couple things. It can mean, first of all, that our work in our previous labs has been inaccurate. It also can mean that there's a lot of error, which I'll get into. I don't know which one is correct, but I think that our first model with our 1.952 mu is definitely incorrect. So yeah, I was talking about our sources of error. So our first is just that there is some inevitable contact between the magnet and the tube. When I was dropping it down, I noticed that it kept brushing the sides a bit, which is obviously expected, but the friction is an additional force, and that would also increase the time that it would take to pass through the tube, which then would account for why in our computational model it says it would have taken a shorter amount of time because it wasn't taking into account friction. Also just timing inaccuracies, because we are all human, and just pressing start and stop on a watch isn't always the most accurate way of measuring things, especially when you have to rely on your eyes. And then finally, we have some measurement errors. We were a bit unclear on where we're supposed to measure our aluminum foil. Is it just the inside or just the outside or the entire thing? So I'm sure that could have also played a role. So for our two what if questions, we have what if the resistivity of the conductor was reduced to zero, essentially. So this is a really interesting question because it goes back to Ohm's law, where we're looking at how resistivity relates to current. So if the resistivity is zero, essentially our current is going to be very, very large. And then what if holes were cut into the tube? How would this affect the ring currents in our model? So it would essentially disrupt the continuation of the rings, and it would allow for the induced current to flow around the tube as the magnet falls. So as a result, the overall magnetic force would decrease, so the magnet is going to fall with a greater speed and in less time.